Hi, this is Wentao Yan from the National University of Singapore. Today, I will talk about our work on high-fidelity multi-physics modeling of process structure property relationships in additive manufacturing. So these works are mainly done by myself and my group members listed here. So the questions we want to answer through multi-physics modeling, including what's happening outside, like powder motion, surface roughness, and what's happening inside, like pores, voids, and grain structures, and ultimately, what are the mechanical properties? Correspondingly, we have developed a series of models, like multi-scale modeling of melting processes, the powder dynamics models, grain evolution models, and then we integrated the process structure property models together. So our contributions lie on developing a complete simulation chain of manufacturing, microstructure, property for the relationships. But the focus today will focus on the multiple dynamics model, including how it's linked with the DM model of powder spreading, the physics-based heat source models, the composition-dependent evaporation model, effects of external magnetic field, effect of ultrasound, and also I will talk a little bit about multi-material melting model. So then I will also talk about our work on microstructure evolution models from grain growth to dendrite growth, and also multi-scale thermostress models from meso-scale to microscale. So the overall framework is like this. When we get the fabrication parameters, we use the powder spreading model and powder melting model to simulate the manufacturing process so that we can predict the temperature profile and void formation. Then we input in to the cellular automaton and cellular and phase field models to predict microstructure evolutions. Further, we can use crystal plasticity model to predict the mechanical properties and thermal stresses. With that, we can replace most of the trial and error experiments and accelerate the R&D process. And for the manufacturing processes, there are two major procedures. First is apply a powder layer. Second is the powder melting process. So correspondingly, we built two models for powder spreading using the discrete element method and powder melting using the computational fluid dynamics. So in the powder spreading model, we include the elastic, inelastic collisions, friction, gravity, and also van der Waals force. And we can investigate the influence of the rake shape, speed, layer thickness, and powder size distribution. So with this model, we can get the configuration of the powder bed, implement into the powder melting model to simulate the powder melting process, which can simulate the solidified geometry. And then we repeat these processes by coupling these two models together. We can repeat what's going on in the real experiments. For the powder melting model, in addition to generating realistic powder bed geometry, we can also use this model to better understand and optimize the powder bed quality, like packing density and surface roughness. And also we can provide guidance for the design and selection of a variety of parameters, like the shape of the powder rake or roller, spreading or rotating speed, powder size distribution, and layer thickness. So there are mainly two types of powder spreading machines. First one is rake type. The rake is translating over the powder bed. Another is roller type powder spreading, where the roller is rotating and translating. We have done extensive experiments to validate these models. Like this, for the roller type powder spreading, we add a portfoliometer here so that after powder spreading, we can in situ measure the surface configuration of the powder bed so that we can evaluate the relative, the surface roughness. And after this process, we can collect the powder and measure the relative packing density of the powder bed. And then we can do quantitative comparison for the simulation. And for the powder melting model, another very important factor is the heat source. And traditionally, a lot of heat source is based on assumption and simplifications. But here, to improve the accuracy and fidelity, we get this heat source model directly from the fundamental physics. For electron beam, it's the interactions between the free electrons and material atoms. We use Monte Carlo method to simulate millions of free electrons impinging into the materials can collide with the different atoms in the material. During the process, we check the trajectories of the free electrons and also record the energy transfer between the free electrons and material atoms so that we can get a physically informed heat source model, including the distribution in the cross-section, the energy distribution along the penetration depth, the energy absorptivity. And then one group in Canada, they use the same model as us and did some experimental validation. And you can see at different incidence angle, the energy absorptivity is very close to the simulation, which demonstrates the validity of the model. The next question is how to do multi-scale modeling by implement the micro-scale simulation into meso-scale or powder-scale simulation for the powder melting process. So first in the powder melting process, we reconstruct the free surfaces based on the VOF method like this, and then we apply our heat source model by dividing the electron beam into a number of subbeams with varied energy. And for each subbeam, the penetration starts from the surface, and the energy absorptivity is different for different subbeams depending on the incidence angle. And also the energy distribution along the penetration distance is applied based on the micro-scale model. And also we can apply recoil pressure and evaporation on the reconstructed surface, which is temperature dependent and composition dependent. So after this, we update the free surface at the end of each time step. So this is a showcase. We assume it's a uniform distribution in the cross-section of the electron beam, incidence on the spherical particle. And you can see the incidence angle is 0 here in the center and become larger and larger to the edges. So the energy absorptivity is highest in the center and become lower and lower to the edges. So that's the reason why the incidence, the particle get melted in the center first and then the edges. And for commonly seeing Gaussian distributed electron beam, if the power is high enough, the recoil pressure will be dominant so that you can see the keyhole formation. And for laser, the heat source will be totally different because for laser, there will be multiple reflection because energy absorption for each interaction is much lower. So we consider this this heat source model as using the retracing method to track the multiple reflection And for each reflection, the energy absorptivity is calculated based on the Fresnel equation, which is essentially from the Maxwell equation. You can see we can consider the energy absorptivity for different materials with different wavelengths and polarization. And also the influence of incident angle is also considered. And this is a verification case. We assume a laser coming from here. And you can see the simulation results like here. And you can see the trajectory of the laser is the same as expected. And also the first irradiation spot get melted, and then the second one you can see obvious temperature rise, and third one you can see the temperature rise but lower, and the fourth one you can barely see the temperature rise. This due to the energy of the laser become lower and lower. So which demonstrates the validity of our implementation of the Higgs model. With that, we can simulate the very common phenomena like how non-uniform tracks or balling effects happen. And we can review the fundamental physical mechanisms, which is actually mainly driven by the surface tension. But essentially, it's influenced or determined by the energy density. And we also do quantitative validation in collaboration with the US National Institute of Standards and Technology. So to scan a single track, so there are actually different scan strategy. One scan strategy is called exact stop, but that means we turn on the laser and laser scanning at the same time. But the laser scanning is controlled by a gavel mirror, and it's a mechanical system, so there has to be an acceleration and deceleration stages. So in this acceleration and deceleration stages, the energy density will be different from the constant speed stage. So another strategy called constant speed, where we just turn off the laser during the acceleration and deceleration stages. Another scan strategy called continuous scan, where we just change the laser scan direction in the beginning and ending. So this is blue lines are the experimental results. So it's a surface elevation along the track. And the black lines are the simulation results. And you can see the surface elevation is between around 10 micrometer in the beginning at the peak, and around 10 to 15 micrometer in the end. So these are due to the Marangoni effect. And our simulation can well reproduce the peak and valley, and quantitatively, the absolute error between simulation and experiments is within 2 micrometer, because our simulation mesh is about 4 micrometer. And also we validated our multiple weights that's here. And you can see there are a large peak in the beginning and a small peak in the ending. And our simulation can reproduce both peaks, and also we can compare quantitatively the mean value and standard deviation, and they all agree well between simulation and experiments. And for more complex cases, like multiple layer, multiple tracks, this is a reason how, where the interlayer, intertrack voids will be formed. So no matter what the scan path is in experiments, maybe like this, in one layer and next layer, it will tend for a certain angle, we can well reproduce it in our simulation. And this is a free surface view. Here you can see the formation process of the lacquer fusion voids. And actually the shape, size, and space distribution of the lacquer fusion voids, they all agree well with our experiments. And if it's for laser powder fusion, mostly it's keyhole mode. And for keyhole mode, the evaporation is very serious. So, but traditional models didn't consider the compositions. So here we develop our own composition-dependent evaporation model based on the Maxwell equation distribution for molecule distribution, Boltzmann equation for molecule collision, and also the boundary conditions where we consider the compositions. And then we validate our model against the in situ X-ray imaging results by Argonne National Lab. Now you can see this is the similar results using our own evaporation model. And this is a traditional evaporation model developed by NUS in 1970s. So you can see the difference of the development of the keyhole. And this you can see our simulation is closer to the experiments because the recoil force is different. And basically our evaporation model is physically more rigorous and has wider application to different materials and different ambient pressure, and also have better accuracy. This is the laser scanning cases. So we, in collaboration with Argonne National Lab, we also simulate this, and you can see actually the keyhole size and shape and the molten pool shape and size all agree well between the simulation and experiments. But more importantly, we can provide some information that can hardly be measured even in Argonne. That is the energy absorptivity at different locations. You can see the energy absorptivity at different locations is fluctuating all the time because they are directly related to the keyhole shape. You can see when the keyhole is shallow, the energy absorptivity is low because there will be fewer laser reflections. And when the keyhole depth is larger, then the energy absorptivity will become larger because there will be more reflections within the keyhole. And even for the same laser power, same powder bed, but with different scan speed or the same scan speed with different power, the energy absorptivity can be different. Now you can see our simulation agree well with the experiments, both like the depth and inclination angle. And more importantly, we can show the energy absorptivity. Actually, they are influenced by the laser power and the scan speed. So furthermore, we can simulate the keyhole pore formation. And in the X-ray imaging results by Argonne National Lab, they can observe 3 different stages for the keyhole pore formation. And our simulation exactly reproduce these 3 stages. The first stage is a protrusion process where it forms a new keyhole called newborn keyhole, and this newborn keyhole will close the previous keyhole. So this part, the laser cannot reach, and then the energy will be reduced. So there will be a clap. So it's keyhole clap here, and then form a keyhole pore. And besides this, we can further review the driving force, which is actually the recoil pressure. And furthermore, this recoil pressure is driven by the energy. Okay, and you can see the rear keyhole will absorb more energy, but the fluctuation is also larger. So it leads to larger fluctuation of the rear keyhole wall, which lead to the keyhole pore formation. And for the keyhole pore size, it also agree well between our simulation and experiments. And you can see this is around the threshold value for the keyhole pore formation. And it's very sensitive to the input energy in this area. And the next question is, how can we eliminate or eliminate the keyhole pore or manipulate the molten flow? So one popular approach is to add an external magnetic field. And it has proven very effective in experiments, but the understanding of how it works is still lacking. So here we developed our model to incorporate the effect of magnetic field by incorporating the Ohm's law Seebeck's effects, then the Lorentz force on within the molten pool. And we simulate different cases without magnetic field, 0.4 Tesla around the y direction, 0.4 Tesla around z direction. And you can see the molten pool length will be influenced by the magnetic field as well as the keyhole depth. But this is not so significant. So what's significant is the molten flow patterns. And you can see without magnetic field, there are two vertices in the molten pool. One is near the keyhole, another is in the rear part of the molten pool. And with these two vertex, when there's a keyhole pore forms in this area, then it cannot escape because this vertex near here will keep circulating the pore within the keyhole. But when we add an external magnetic field, we can eliminate this vertex in the rear part of the molten pool. So when there's a keyhole pore being formed here, it can escape due to this flow pattern in the rear part of the molten pool. And also the Lorentz force near the molten pool boundary is strong enough to the criteria that experimentalists found in experiments, which can potentially refine the grains. And for the powder melting in multi-material additive manufacturing, which is very promising in material design. So actually there are two scenarios based on our consideration. One is all the powders is melted. That is actually in situ alloying. Now, there are a few physical phenomena influence the chemical composition, which should be considered. One is convection, but for diffusion, it's usually minor, and the rapid melting and solidification. And elemental mass loss due to evaporation is also serious. Another important factor is the thermal properties, which are composition dependent, should be calculated. When we actually couple the CalFET approach with our model. Another scenario is one type of the powder cannot be melted. That is like particle reinforced composites. And based on the particle size, it can be microparticle reinforced composites, nanoparticle reinforced composites. And nanoparticles can refine grains. So we'll talk a little bit about work on this. So this is one example. So this is very complex high entropy alloy, and the manganese concentration in the powder is around 34 weight%. But with different laser melting parameters, we can see this concentration is varying with locations and also the manufacturing parameters, because manganese have different manufacturing, have different evaporation rate with other chemical elements. And these are experimental results. And you can see the as-built part with different manufacturing parameters, the magnetic concentration are different. And our simulation agree pretty well with the experimental results. Another case is nitinol powder on titanium base plate. So these are basically, there are two different materials. And for this keyhole regime, there are the chemical element distribution is very complex. Now you can see there's a keyhole pole here in the experiments, and then there will be segregation line in the middle of the keyhole. Now you can see in our simulation, we also reproduce this phenomena, and including both the keyhole and the segregation line. Another scenario is a particle reinforced composites. So this is one example of a microparticle of tungsten reinforced copper composites. So the gray particles are the tungsten particles. They cannot be melted, where the copper matrix can be melted. And also the copper powder can be melted. And you can see all these tungsten particles are floating on the surface of the molten pool surface. And just a few tungsten particles can submerge into the molten pool. Now you can see this is experimental validation. So in single tracks, these tungsten particles are mostly on the surface, and they are not uniformly dispersed. In addition to the pod bed fusion process, we also have the models for directed energy deposition process. So no matter it's a single track or multi-layer, multi-track, or no matter it's straight track or curved track, we can easily reproduce it in our simulation. And a popular way to manipulate the molten pool flow and the grain structure and mechanical property in this DD process is to add ultrasound. But how ultrasound manipulate the molten pool flow is rarely understood. So we use a high-speed camera to observe the molten pool flow, and also we run the simulation by incorporating the ultrasound effects in our model. And you can see the fish scale ripples on the molten pool surface, right? And this agrees perfectly with the experimental validation. And in pod bed fusion, there's another important phenomenon called powder spattering and denudation. So during laser scanning, you see the laser is blow up, and some of the powder is also moving all the time. So we build a multi-phase flow model to reproduce this phenomena. You can see we decouple from the multiple flow model. We just consider the vapor jet and their interactions with ambient gas and the pod particles. You can see our similar results reproduce these experimental observations. But more importantly is our model can provide more information that cannot be measured in the experiments. For example, like the ambient gas velocity, temperature, the particle velocity and temperature. And in experiments, when we use different manufacturing parameters, there will be different behaviors of powder spattering and denudation, and we can reproduce in our simulations. Other additive manufacturing processes like extrusion, material extrusion AM process, or like fused filament fabrication, where the non-Newtonian fluid flow and heat transfer are incorporated. We can simulate in our model. Even it's not just a polymer flow. There are reinforcing short fiber inside. We can also simulate their interactions and also the heat exchange between them, so that we can predict the orientation and distribution of the short fiber in the as-built part. Another very popular AM process is binder jetting. So it's even more complex, including fluid flow, heat transfer, fluid particle interactions, and particle-particle interactions. So we can reproduce all the phenomena like binder wetting and spreading, and as well as the powder spattering and agglomeration. So this is validation against the high-speed X-ray imaging in Argonne National Lab. So the average particle spattering velocity is pretty close, and also the spattering velocity distribution is also similar. And furthermore, we would explore the microstructure evolution and thermal stress. So the idea is simple. We just implement the temperature profile from the powder melting model into the grain growth model. In this model, our unique contribution is we comprehensively incorporate a classic nucleation model, where this like pink dots are the possible nucleation sites, and we implicitly track them so that we can consider the nucleation rather than pre-assign nucleation seed. And these are experimental validation. So the grain morphology and size all agree well with the experiments. And furthermore, to refine the grains, experimentalists like to add nanoparticles inside. And how nanoparticle can refine the grains? So there are actually two effects. One is in the nucleation, they can introduce more nucleation sites. And second is during the grain growth, they can slow down the grain boundary movement so that they can slow down the grain growth. So which is called Zener-Pinning effect. So we incorporate both effects in our simulation, and then we do the simulation compare with experiments. So when there's no nanoparticle, you can see it's mostly columnar grain. And with addition of nanoparticles, it's a short columnar grain in the boundary and the equal axis grains in the middle. So this agree well with the experimental results in literature. And also we compare quantitatively on the grain aspect ratio and grain size. But for even smaller scale, in Dendrite scale, that is where the solidification defects happens. So to do that, we develop a new model to simulate the dendrite growth with arbitrary orientations. And then we compare this model against some classical models like KGT model and LGK model, something like that. And then we compare with X-ray imaging results for a simple case casting. This is a simulation results, and this is a X-ray imaging observation. And also this is a dendrite growth rate. But this is still insufficient for validation because in casting, the cooling rate and temperature gradient are much smaller than those in additive manufacturing. So we further validate our model against the electron beam additive manufacturing experiments. And in different locations, the cooling rate and temperature gradients are different. So we extract the thermal conditions for the dendrite growth simulation and then validate in terms of the primary dendrite arm spacing and also the solute distribution across the dendrites. So they agree well. And furthermore, based on the dendrite growth model, we can indicate how the shrinkage pores are formed. So there are actually two types of formation mechanisms. One is where there is no misorientation. So all the shrinkage pores are regularly distributed and their shape are spherical. In another scenario is there are misorientation between dendrites. So these shrinkage pores are irregular shape and also they are not irregular. They are irregularly distributed, and they appear with solute-rich precipitates. So furthermore, with the microstructure model, we can from either like grain growth model or experimental data, we can construct the microstructure geometry and use crystal plasticity model to simulate the mechanical behavior and do experimental validation. But here, what I want to show is the importance of the residual stress. And you can see during tension and compression tests for the same batch of samples, the yield stress has a difference around 400 megapascal for this titanium sample, and which is very significant. This is due to the large reduced stress in additive manufacturing. So to simulate this, we input the temperature profiles from the thermal fluid flow simulation results into a finite element solver to implement the accurate temperature profile and also the realistic geometry, including voids and rough surfaces, so that we can improve the prediction accuracy of thermal stress and deformation. In comparison, you can see this is a conventional thermal stress model where the surfaces are perfectly flat and the temperature profile are not so accurate. Then the accuracy may be relatively big. So with this, we can very well explain the experimental observation how of the cracking happens. So when the laser just passed by, there's no cracking, right? Because it's compression stress. And when it go further, it's still compressive stress. But when it's go even further and it's further cooling down, there will be cracks here. This is because one is the thermal stress become tension. Second is due to the rough surfaces, there's stress concentration, which lead to cracking. But this is just a qualitative comparison. For quantitative comparison, it's still very difficult. And in even smaller scale, in grain scale, actually the thermal stress or reduced stress vary across different grains. And this is the origin of micro cracks. And to address this challenge, we actually implement both the temperature profile and grain structure into a crystal plasticity model to simulate the micro-scale reduced stress. And also we consider the cooling process where the thermal stress will be relaxed into the reduced stress, and we compare with the experimental results in literature. So that's pretty much all of high fidelity models. You can see they are high fidelity, high accuracy, but also have high computing cost. So what's the solution? I think the solution is data-driven surrogate modeling. So this is just one example. We can use the high fidelity model as a training data, then use machine learning or regression algorithms to develop surrogate models so that then we can further implement this temperature profile into different subsequent models. Then actually, this model will have accelerate or reduce the computing cost by at least 99%. And for this, we can also accelerate at least to 90%, reduce the computing cost by 90%. So that's all for my presentation today. Thanks for your listening. And if you are interested, you can read our papers